Richard Feynman approached the idea that space and time are not separate realities with a kind of intellectual honesty that stripped away unnecessary mystery. He did not ask people to believe this idea because Einstein said so, or because equations demanded it, but because nature itself behaves as if space and time are deeply connected. For centuries, human beings lived comfortably with the assumption that space was a fixed stage and time was a universal clock. Space was thought of as something solid and unchanging, an invisible container in which all motion occurred. Time, on the other hand, was imagined as a steady river flowing at the same rate for everyone, everywhere. Feynman explained that this picture feels natural because it matches everyday experience, but physics is not built on what feels natural. It is built on what experiments reveal. He emphasized that the separation of space and time works only when things move slowly and when precision is not critical. In ordinary life, the difference between 1 second here and 1 second somewhere else is too small to matter. But when scientists began measuring nature more carefully, and when they started observing objects moving at enormous speeds, cracks appeared in the old framework. Experiments showed that time could not be the same for all observers. Clocks, moving relative to one another, tick at different rates, and this difference is not due to faulty machinery. Feynman made it clear that if all clocks are built correctly and treated fairly, the disagreement remains. This forces a radical conclusion. Time itself depends on motion. Once time loses its universal status, space cannot remain untouched. Feynman explained that measurements of distance also depend on motion. Two observers moving relative to each other will not agree on the length of an object. Again, this is not because rulers physically shrink in some mechanical way, but because space itself is measured differently depending on the observer's state of motion. These two facts, time dilation and length contraction, are not separate tricks. They are two sides of the same deeper truth. Space and time are linked. Feynman often pointed out that the real breakthrough was not discovering that clocks run slow or rulers get shorter, but understanding why they must do so. The reason lies in the constancy of the speed of light. Experiments show that light travels at the same speed for all observers, no matter how fast they are moving. This single fact destroys the old separation between space and time. If time were absolute, then speeds would add up in a simple way, and different observers would measure different speeds of light. Since this does not happen, space and time must adjust themselves to preserve the same speed of light for everyone. Feynman loved how this idea showed nature's consistency. The universe keeps one rule fixed, and everything else reshapes itself around that rule. To make this understandable, Feynman encouraged people to stop thinking of space and time as independent entities. Instead, he suggested thinking in terms of events. An event is something that happens at a particular place and at a particular time. You cannot separate the two without losing information. Saying that something happened there is meaningless unless you also say when. Likewise, saying it happened then is incomplete unless you specify where. Physics, at its core, deals with relationships between events, not with isolated measurements of space or time. By combining space and time into a single framework, space-time, physicists gained a clearer and more powerful way to describe reality. Feynman explained that in this framework, different observers may slice space-time differently. One observer may call two events simultaneous, while another observer, moving at a different speed, may say they occurred at different times. This is not a contradiction. It simply reflects that simultaneity itself is not absolute. What matters is not agreement on time alone or space alone, but agreement on the underlying structure that connects events. Feynman was careful to stress that this does not mean everything is relative in a vague or philosophical sense. There are quantities in space, time that all observers agree on. One of these is the space-time interval between events. While observers may disagree on the time difference or the spatial distance between two events, they will calculate the same space-time interval. This invariant quantity replaces absolute space and absolute time as the fundamental measure of reality. Feynman admired this because it showed how nature replaces old absolutes with deeper, more subtle ones. He also addressed a common misunderstanding, that space, time is something physical, like a rubber sheet floating in a higher dimension. Feynman warned against taking metaphors too literally. Space, time is a model, a mathematical structure that helps us organize observations and make predictions. It is not something you can step outside of or see from the outside. The value of the model lies in its ability to explain experiments consistently, not in how easily it can be visualized. In Feynman's style, he often returned to the idea that physics is about describing how nature behaves, not about satisfying intuition. The idea that space and time are inseparable feels strange only because human intuition evolved in a slow, moving world. Nature itself has no obligation to match that intuition. When experiments force us to abandon comfortable ideas, the correct response is not resistance, but curiosity. Space-time is not an invention designed to confuse, it is the simplest way to make sense of what nature is doing. By uniting space and time, physics gained a language capable of describing motion, causality, and the limits of influence in the universe. Signals cannot travel faster than light, and this limit is built directly into the structure of space-time. This means that not all events can affect one another. Some are forever separated by the geometry of space-time itself. Feynman found this deeply satisfying because it showed that the universe has built in order, not imposed from outside, but arising naturally from its structure. In this view, space and time lose their independence and gain something greater coherence. They become aspects of a single reality that responds to motion and preserves fundamental laws. Feynman's explanation of this first keynote leaves us with a profound shift in perspective. Space is not just where things are. Time is not just when things happen. They are intertwined aspects of how events exist, relate, and unfold. Understanding this is not merely a technical achievement, it is a change in how we think about reality itself. Feynman continued to deepen this idea by showing that once space and time are joined, many puzzles that once seemed impossible suddenly become simple. He often emphasized that confusion in physics usually comes from insisting on the wrong categories. Treating space and time as separate boxes creates contradictions that disappear the moment they are treated as one structure. Nature, he explained, does not experience space first and then time afterward. Events simply occur, and space, time is the bookkeeping system that keeps track of them in a way that works for everyone. He illustrated that when we insist on absolute time, we are secretly assuming a universal agreement that nature never promised. Two observers, moving differently through the universe, carry their own clocks and rulers, and these tools are part of the universe, not outside it. When their measurements differ, it is not a failure of reality, but a reflection of how reality is organized. Feynman stressed that physics does not ask whose measurement is correct, it asks what rule connects them. Space, time provides that rule. One of the most striking consequences Feynman liked to highlight is that motion through space and motion through time are linked. An object at rest in space is moving entirely through time. An object moving rapidly through space moves more slowly through time. This is not a metaphor but a precise statement within the space-time framework. Every object traces out a path through space-time, called its history, and the shape of that path determines how much time the object experiences. This idea replaces the old notion of time as an external flow with the idea of time as something that depends on the path taken through space-time. Feynman often pointed out that this perspective removes the need for hidden mechanisms. There is no need to imagine time being slowed down by some force or clocks being interfered with. Clocks simply follow different paths through space, time, and those paths naturally involve different amounts of time. In this sense, time dilation is not something that happens to clocks. It is something that happens to paths. This shift in thinking is subtle but powerful, and Feynman believed it was one of the clearest examples of how physics simplifies when the right concepts are used. He also emphasized that space-time forces us to rethink simultaneity. In everyday thinking, we assume that if two things happen at the same time for one person, they happen at the same time for everyone. Feynman explained that this assumption has no experimental support once motion is involved. Simultaneity depends on how an observer moves. Different observers divide space-time into space and time in different ways, much like different people might slice the same loaf of bread at different angles. The loaf is the same, but the slices differ. Space-time remains intact, only the perspective changes. This led Feynman to a crucial point. Disagreement between observers is not a flaw but a feature. Physics is designed to accommodate these differences without collapsing into chaos. The laws of physics are written in a way that does not depend on any single observer's division of space and time. By expressing laws in terms of space-time relationships, physicists ensure that everyone, regardless of motion, can use the same laws and obtain consistent results. Feynman admired this deeply, seeing it as evidence of nature's elegance. He was also careful to address the emotional resistance people often feel toward these ideas. Humans like the comfort of a single, now, a shared, present moment across the universe. Space-time takes that comfort away. There is no universal present slicing across all of space. Instead, each observer has their own present, defined by their motion. Feynman did not see this as disturbing, but as liberating. It frees physics from unnecessary assumptions and allows it to reflect the universe more accurately. Feynman often reminded his audience that space-time does not mean the universe is frozen or predetermined. Even though space-time can be pictured as a four-dimensional structure, this does not eliminate change or choice. Events are still experienced sequentially by observers. The space-time description simply records the relationships among those events. Confusing the map with the territory, he warned, leads to philosophical mistakes. Space-time is a way of describing events, not a claim that the future is already experienced in the same way as the past. Another key insight Feynman emphasized is that space-time naturally encodes limits. Because the speed of light is built into its structure, space-time determines which events can influence each other. Some events are too far apart in space-time to be connected by cause and effect. This is not a technological limitation but a fundamental one. No matter how advanced a civilization becomes, it cannot bypass the geometry of space-time. Feynman saw this as a profound statement about the universe. It has rules that are not imposed externally but arise from its very structure. He also highlighted how space-time unifies seemingly different phenomena. Motion, time measurement, distance, and causality all emerge from the same framework. This unification is what made space-time such a revolutionary concept. Instead of separate explanations for each effect, one structure explains them all. Feynman believed that this kind of unification is the hallmark of good physics. When one idea explains many things, it is usually pointing in the right direction. Despite all its power, Feynman remained humble about space-time. He reminded listeners that it is still a model, refined and tested, but not sacred. If future experiments demand a deeper or different framework, physics will adapt. What matters is not loyalty to a concept but loyalty to nature. Space-time is accepted because it works, because it predicts outcomes correctly, and because it reveals connections that were previously hidden. In closing this exploration of the first keynote, Feynman's perspective leaves us with a transformed understanding of reality. Space and time are not separate backdrops against which life unfolds. They are intertwined aspects of a single structure that shapes motion, measurement, and causality. By accepting this, we move closer to how nature actually operates rather than how we instinctively imagine it should. Space-time does not remove mystery from the universe, it replaces confusion with clarity, and in doing so, opens the door to even deeper questions about the nature of existence. Richard Feynman often explained that once space and time are understood as a single structure, the next unavoidable realization is that motion fundamentally changes how that structure is experienced. Motion is not just something that happens within space-time. It determines how each observer cuts space-time into what they call space and what they call time. Feynman emphasized that this idea is not philosophical speculation, but a direct consequence of experimental facts. When objects move relative to one another, their measurements of time and distance differ in precise, predictable ways. These differences are not errors. They are the correct descriptions from each observer's point of view. He began by reminding people that in everyday life, motion seems simple and harmless. If two people walk past each other, they may disagree about who is moving and who is standing still, but they still agree on the time of events and the size of objects. This agreement breaks down only when motion becomes extremely fast. Feynman stressed that physics does not change its rules at high speeds. Rather, high speeds reveal rules that were always there, but hidden by our limited experience. The universe behaves the same way at all speeds, but our intuition does not. One of the clearest examples Feynman used to illustrate how motion changes experience is time dilation. A moving clock runs slower compared to a clock at rest, as judged by an observer. Feynman took care to explain that this is not because the clock is damaged, or because motion physically interferes with its mechanism. Any process that measures time, whether mechanical, electronic, or biological, will slow down in the same way when moving. This includes atomic vibrations, chemical reactions, and even aging itself. Motion affects time, not devices. He emphasized that this effect is symmetrical. Each observer sees the other's clock running slow. This symmetry often confuses people, but Feynman explained that there is no contradiction because each observer is using their own definition of simultaneity. Without a universal time, there is no single answer to the question of whose clock is really slow. Physics does not ask for such an answer because nature does not provide one. What physics provides instead are transformation rules that relate one observer's measurements to another's. Length contraction is the spatial counterpart to time dilation. Feynman explained that an object moving relative to an observer is measured to be shorter in the direction of motion. Again, this is not because the object is being crushed or deformed. In its own rest frame, the object has its normal length. The difference arises from how space and time are mixed together when measurements are made. Measuring length requires determining the positions of both ends of an object at the same time. Since simultaneity depends on motion, length depends on motion as well. Feynman enjoyed pointing out that time dilation and length contraction are not independent effects. They are aspects of the same underlying structure. When motion changes how time is experienced, space must adjust accordingly to keep the speed of light constant. This interdependence shows that space and time cannot be separated. Motion reveals their connection in a concrete, measurable way. He often stressed that none of these effects are matters of perception or illusion. They are real in the sense that they affect outcomes of experiments. Particles moving at high speeds live longer than they would at rest. GPS satellites must account for time dilation to provide accurate positioning. These are not philosophical curiosities, they are practical consequences of how motion reshapes experience within space-time. Feynman also explained that the idea of a preferred state of rest is unnecessary. There is no absolute background against which motion can be measured. All motion is relative. What matters is not how fast something is moving in an absolute sense, but how fast it is moving relative to an observer. The laws of physics take the same form in all inertial frames, meaning frames moving at constant velocity. Motion does not break the laws, it reveals their deeper symmetry. Another key point Feynman emphasized is that observers moving differently through space-time follow different paths, and those paths determine how much time they experience. This leads to scenarios where two observers separate and later reunite, having experienced different amounts of time. Feynman explained such situations not as paradoxes, but as natural consequences of differing paths through space-time. The path taken matters, not some imagined universal clock. He also highlighted that motion through space-time is unavoidable. Even an object, at rest, is moving through time. Motion through space reduces motion through time, and vice versa. This balance is built into the geometry of space-time. Feynman liked this idea because it replaced vague notions of time slowing down with a precise geometric picture. Objects are not losing time. They are simply following different routes through space-time. Feynman made it clear that understanding how motion changes experience requires letting go of everyday language. Words like simultaneous, before, and after carry hidden assumptions rooted in human experience. Physics forces us to redefine these words or use them more carefully. Events that are simultaneous for one observer may not be simultaneous for another. Motion reshapes the ordering of events, but only within the limits set by the speed of light. Despite the strangeness of these ideas, Feynman emphasized their simplicity at the core. There is one rule: the laws of physics, including the speed of light, are the same for all observers moving at constant velocity. Everything else follows from this. Motion does not complicate the universe, it reveals its structure. What seems strange is only strange because we are used to slower speeds. He also stressed that these effects do not mean reality is subjective in a careless sense. Observers may disagree on measurements, but they agree on the rules connecting those measurements. This agreement is what allows physics to function as a universal science. Motion introduces differences, but space-time provides consistency. In Feynman's view, the study of motion in space-time teaches humility. It reminds us that human intuition is limited and shaped by environment. The universe operates on principles that remain consistent across all speeds, even when those principles challenge our everyday understanding. Motion is not a complication added to physics. It is the key that unlocks the true nature of space-time. By recognizing that motion changes how space and time are experienced, we gain a deeper appreciation of reality's flexibility and order. Space-time is not a rigid grid, but a dynamic structure that responds to motion while preserving fundamental laws. Feynman saw this not as a loss of certainty, but as a gain in understanding, revealing a universe that is more subtle, more consistent, and more beautiful than common sense ever suggested. Feynman expanded this discussion by showing that motion does more than alter measurements, it reshapes the very way reality must be described. He emphasized that when different observers move relative to one another, they are not merely disagreeing about numbers on clocks and rulers, they are experiencing different decompositions of the same underlying space-time. This idea helps dissolve many apparent paradoxes. What looks contradictory when space and time are treated separately becomes natural when they are understood as parts of a single structure affected by motion. He often returned to the idea that physics should not privilege one observer over another. There is no cosmic referee standing still somewhere in the universe, deciding whose measurements are correct. Each observer carries their own frame of reference, and the universe respects all of them equally. Motion does not create an error, it creates a different perspective. Feynman saw this as a profound democratic principle of nature. Every inertial observer has the right to describe the universe using the same laws, even if their experiences of time and space differ. Feynman liked to explain that the mathematical rules connecting these perspectives are not arbitrary. They are precise and rigid. When one observer calculates how another observer's clock runs or how their measuring rods behave, the result always follows the same transformations. These transformations ensure that physical laws remain consistent. Motion introduces differences, but those differences are tightly constrained. This balance between freedom and restriction is one of the reasons Feynman found relativity so intellectually satisfying. He also clarified that motion's influence on time and space is not gradual in the way people often imagine. It is not that time slowly begins to behave differently once some threshold is crossed. The effect exists at all speeds. Even at walking speed, clocks tick differently, but the difference is so small that it escapes notice. Feynman stressed this point to show that relativity is not a special theory for extreme situations, It is a universal description that applies everywhere, all the time. Another idea Feynman emphasized is that motion forces us to rethink the concept of duration. The amount of time an observer experiences between two events depends on the path they take through space-time. Two observers can start together, separate, and meet again, each having experienced a different duration of time. This is not because time itself is inconsistent, but because duration is not an absolute quantity. It is linked to motion, just as distance is linked to the path taken through space. Feynman rejected the word paradox for such situations. He argued that paradoxes arise only when old assumptions are mistakenly applied to new frameworks. Once the assumption of universal time is removed, the situation becomes straightforward. Each observer's experienced time is simply the length of their path through space-time. Motion determines that path, and geometry determines the result. Nothing mysterious remains. He also pointed out that motion changes not only how much time is experienced, but how events are ordered. For events that cannot influence each other, different observers may disagree about which happened first. Feynman emphasized that this disagreement has no physical consequence because causality is preserved. Events that can influence one another always maintain the same order for all observers. Motion may rearrange the sequence of distant events, but it cannot create contradictions in cause and effect. This insight led Feynman to stress that space-time places firm limits on what motion can do. No amount of motion can allow information to travel faster than light. No observer can rearrange cause and effect. The structure of space-time protects consistency. Motion introduces flexibility in measurement, but not chaos. Feynman believed this balance was one of the strongest arguments that relativity reflects something real about the universe, not just a clever mathematical trick. He also connected motion to energy and mass. As objects move faster, their resistance to acceleration increases. Feynman explained that this is not because mass is literally piling up inside the object, but because accelerating an object at high speed requires changing its path through space-time in a way that becomes increasingly difficult. Motion alters how objects respond to forces, further demonstrating that space-time is not a passive backdrop. Feynman liked to remind his audience that these ideas were not dreamed up in isolation. They were forced upon physicists by experiments. Particles created in the upper atmosphere reach the Earth's surface because their motion through space-time allows them to experience less time before decaying. Technologies that rely on precise timing must account for motion to function correctly. Motion's effect on time and space is woven into the fabric of modern science and technology. Despite this, Feynman acknowledged that accepting these ideas requires intellectual discipline. Human intuition resists them because it evolved in a narrow range of conditions. Motion at relativistic speeds was not part of everyday survival. Physics, however, is not bound by biological intuition. It follows evidence wherever it leads. Motion reveals that the universe is more flexible and more constrained than intuition suggests, both at the same time. He also emphasized that motion through space-time is not something optional. Everything moves through space-time at all times. Even when an object appears motionless in space, it is moving through time. The difference between observers is how this motion is divided between spatial movement and temporal progression. This division changes with motion, but the underlying structure remains intact. Feynman found beauty in this idea because it replaced static notions with dynamic ones. Reality is not a fixed stage with actors moving upon it. The stage itself participates. Motion reshapes experience without breaking laws. Space-time adapts while preserving its fundamental geometry. This adaptability is not a weakness, it is a sign of a deeper order. As he brought these ideas together, Feynman emphasized that understanding how motion changes experience is essential for understanding modern physics. Without it, concepts like space-time, causality, and energy remain fragmented. With it, they form a coherent picture. Motion is not an inconvenience to be corrected, it is a lens through which the true structure of the universe becomes visible. In the end, Feynman's treatment of motion leaves a lasting impression. Motion teaches us that reality does not offer a single, universal viewpoint. Instead, it offers a consistent set of rules that allow many viewpoints to coexist. Space and time adjust to motion not to confuse us, but to preserve the harmony of physical law. Through motion, space-time reveals itself as a unified, flexible, and deeply ordered foundation of reality. Richard Feynman explained that the speed of light is not merely a detail about how fast light travels, but the central rule that determines how space and time themselves are organized. He emphasized that before this realization, people naturally assumed that speeds simply add together. If someone throws a ball from a moving train, an observer standing still would measure the ball's speed as the speed of the train plus the speed of the throw. This logic works perfectly well in everyday life and seems so obvious that it feels impossible to question. Yet Feynman showed that nature quietly refuses to follow this rule when light is involved. No matter how fast the source is moving, light always travels at the same speed. This single experimental fact forces the universe to behave in a way that defies common sense. He stressed that this constancy of the speed of light is not an assumption chosen for convenience. It is something measured repeatedly and confirmed with astonishing precision. Light does not care whether its source is approaching or receding, whether the observer is moving or standing still. Everyone measures the same speed. Feynman liked to point out how radical this is. If time and space were truly separate and absolute, such a result would be impossible. Something would have to give. Nature chose to preserve the speed of light, and in doing so, it reshaped our understanding of space and time. Feynman often emphasized that the speed of light is not just about light. It is the maximum speed at which information can travel. It defines the ultimate limit of cause and effect. Nothing with mass can reach or exceed this speed, and no signal can outrun it. This limit is not imposed by technology or energy constraints alone. It is woven directly into the structure of reality. Space-time is built around this constant, much like a building is designed around load-bearing columns. Remove the constant speed of light, and the entire structure collapses. He explained that because the speed of light is the same for everyone, measurements of distance and time must adjust to accommodate it. If two observers move relative to each other, and both insist on measuring the same speed of light, then they cannot agree on distances and durations. Feynman showed that this disagreement is not a bug in the universe, but a feature. Space and time are flexible enough to stretch and compress in just the right way to preserve the universal speed limit. This flexibility is not arbitrary, it follows precise mathematical relationships that have been tested again and again. One of the most important consequences of this is that the speed of light replaces absolute time as the fundamental reference. In older physics, time served as the ultimate background against which everything happened. In modern physics, it is the speed of light that plays this role. Feynman explained that instead of asking whether two clocks agree, physics asks whether the speed of light comes out the same in all experiments. Time and space measurements become secondary, adjustable quantities, while the speed of light remains fixed. Feynman also explained that the speed of light gives space-time its geometric structure. Just as geometry on a flat surface differs from geometry on a curved surface, the geometry of space-time differs from the geometry of everyday space. Distances and times are not combined using simple addition. Instead, they are linked through a structure that reflects the constant speed of light. This structure determines which events can influence one another and which cannot. Events connected by signals slower than or equal to the speed of light can be causally related. Events separated beyond that limit are forever disconnected in terms of cause and effect. He emphasized that this has profound implications for how we think about the universe. The universe is not a place where anything can influence anything else if only enough time passes. There are strict boundaries. Some regions of space-time are simply unreachable from others. Feynman found this deeply important because it shows that the universe has built in order. Causality is not a philosophical preference. It is enforced by the speed of light. Feynman often clarified that calling it the speed of light is slightly misleading. Light just happens to travel at this speed because it has no mass. Any massless influence would travel at the same speed. The constant is better thought of as the speed of space, time itself, the conversion factor between space and time. It tells us how many units of space correspond to 1 unit of time in the deep structure of reality. Feynman liked this perspective because it stripped away unnecessary mysticism and replaced it with clarity. He also explained that this constant speed forces us to abandon the idea of instantaneous effects. There is no such thing as an immediate influence at a distance. Even gravity, which once seemed instantaneous, is limited by the speed of light. Changes in gravitational fields propagate at this speed, not faster. Feynman emphasized that this preserves causality and prevents contradictions. The universe does not allow effects to appear before their causes. Another point Feynman made is that the speed of light unifies different observers into a single coherent framework. Even though observers may disagree about times and distances, they all agree on the speed of light. This shared agreement acts as a bridge between perspectives. It allows physicists to write laws that look the same for everyone, regardless of motion. Without this shared constant, physics would fracture into separate descriptions for different observers, losing its universal character. He often returned to the idea that nature is economical. Instead of many arbitrary rules, nature uses a few simple principles to generate complex behavior. The constant speed of light is one such principle. From it flow time dilation, length contraction, the relativity of simultaneity, and the structure of causality. Feynman admired how much explanatory power comes from this single fact. It is not that nature is complicated. It is that we must learn to look at it in the right way. Feynman also emphasized that the speed of light does not slow down or speed up depending on circumstances. It does not get tired, nor does it adapt to our expectations. This stubborn consistency is what makes it so valuable as a foundation. Physics relies on constants because they provide stability. The speed of light is one of the most stable quantities ever measured, making it a reliable anchor for our understanding of space, time. He addressed a common misconception that the speed of light limit is about energy alone. While it is true that accelerating objects to near light speeds requires enormous energy, the deeper reason lies in space-time geometry. As objects move faster, their paths through space-time change in such a way that reaching the speed of light would require an infinite adjustment. This is not merely impractical, it is forbidden by the structure of reality itself. Feynman's explanation of this keynote leaves us with a profound shift in perspective. The universe is not organized around human concepts of distance and duration. It is organized around a constant that links them together. The speed of light defines the shape of space, time, the limits of influence, and the consistency of physical law. It is not just a number, it is a structural rule. In understanding this, Feynman believed we gain insight into how nature thinks, so to speak. Nature does not prioritize convenience or intuition. It prioritizes consistency. By fixing the speed of light and allowing space and time to adapt, the universe achieves a harmony that holds across all frames of motion. This harmony is what makes physics possible as a universal science. This view replaces the comforting simplicity of absolute space and time with something deeper and more powerful. Space and time become flexible, but the laws remain firm. The speed of light stands at the center of this balance, shaping the entire structure of reality. For Feynman, this was not just an abstract insight, it was a demonstration of how a single experimental fact can transform our understanding of the universe from the ground up. Feynman extended this discussion by showing that once the speed of light is recognized as the defining constant of space, time, many seemingly unrelated phenomena fall naturally into place. He emphasized that this constant does not simply sit in equations as a numerical value, it actively shapes what the universe allows and forbids. Every process, every interaction, and every exchange of information must respect this limit. In this sense, the speed of light acts like a set of traffic laws built into the fabric of reality itself. He often pointed out that the existence of a maximum speed has deep consequences for how we think about communication and influence. Messages, forces, and signals cannot leap instantly across space. They must travel, and their travel time matters. This means the universe has a built-in delay. Feynman stressed that this delay is not an inconvenience to be engineered away, it is a fundamental feature. It ensures that the universe remains logically consistent, preventing effects from occurring before causes. Feynman also explained that the speed of light allows us to define what it means for events to be connected. Two events can be connected only if a signal traveling at or below the speed of light could get from one to the other. This simple rule divides space-time into regions of possible influence and regions of permanent separation. Some events lie forever outside each other's reach. This is not due to distance alone, but due to how distance and time combine under the rule of the speed of light. He emphasized that this structure gives rise to a natural ordering of events where causality matters. Events that can influence one another always maintain the same order for all observers. Events that cannot influence one another may appear in different orders depending on the observer's motion. Feynman found this distinction crucial. It shows that relativity does not destroy causality. It protects it by clearly separating what matters from what does not. Another insight Feynman highlighted is that the speed of light gives meaning to the idea of now, only locally. There is no single universal present stretching across the universe. Instead, each observer's present is defined by their immediate surroundings. Distant events cannot be said to be happening now, in any absolute sense, because information about them has not yet arrived. The speed of light enforces this local nature of reality. Feynman saw this not as a limitation of knowledge, but as an honest reflection of how the universe operates. He also connected this idea to the way we construct measurements. When we synchronize clocks or measure distances, we rely on signals that travel at finite speeds. The speed of light sets the ultimate standard for these procedures. Feynman emphasized that our very definitions of time and distance are built around this constant. Space-time is not defined first with the speed of light added later. The speed of light is part of the foundation from the beginning. Feynman further explained that the speed of light allows for a unification of space and time in a quantitative way. It acts as a conversion factor between units of space and units of time. By using the speed of light, physicists can express time in terms of distance or distance in terms of time. This reveals that space and time are not fundamentally different kinds of things, but different aspects of a single entity. Feynman liked this idea because it showed how nature simplifies at a deep level. He also discussed how this constant shapes the behavior of energy and matter. As objects approach the speed of light, their behavior changes dramatically. They become harder to accelerate, and their interactions take on new characteristics. Feynman explained that this is not because the objects are becoming strange, but because the geometry of space-time is asserting itself more strongly. The closer an object comes to the speed limit, the more rigid the constraints become. Feynman was careful to note that the speed of light does not represent a wall in space that objects crash into. It is a boundary in space-time itself. Objects with mass cannot cross it, because doing so would require violating the structure of space-time. This distinction helps clarify many misunderstandings. The limit is not about exhaustion or resistance in a mechanical sense. It is about what kinds of paths through space-time are allowed. He also emphasized that the speed of light plays a crucial role in unifying different forces of nature. Electromagnetism naturally incorporates this speed, and gravity, in its modern description, respects the same limit. Changes in gravitational fields propagate at the speed of light, not faster. This alignment across different phenomena reinforces the idea that the speed of light is not an isolated curiosity, but but a universal feature. Feynman liked to stress that this constant also teaches a lesson about humility in science. Human expectations do not set the rules, experiments do. The discovery that the speed of light is the same for all observers forced physicists to abandon cherished assumptions. Instead of clinging to intuition, they followed evidence. The result was a deeper, more coherent picture of the universe. He also pointed out that while the speed of light is extraordinarily large by human standards, it is finite. This finiteness gives the universe structure and texture. It allows for horizons, delays, and histories. Without it, the universe would be radically different, lacking the rich causal structure we observe. Feynman believed that recognizing this helps us appreciate how delicately balanced the universe is. As he tied these ideas together, Feynman emphasized that the speed of light is not just a constraint but a guide. It tells us how to build theories that respect reality. Any theory that allows faster than light influence must be examined with extreme skepticism because it threatens causality. The speed of light acts as a safeguard, ensuring that physical descriptions remain consistent. In reflecting on this keynote, Feynman's explanation leaves us with a sense of clarity rather than confusion. The universe is not chaotic or arbitrary. It is organized around a small number of deep principles, and the speed of light is one of the most important. By shaping space, time, defining causality, and unifying physical laws, it stands at the core of modern physics. Ultimately, Feynman saw the speed of light as a window into the logic of the universe. It shows how a single, unwavering fact can determine the shape of reality on the largest and smallest scales. Space and time bend, stretch, and adapt, but the speed of light remains fixed, anchoring the entire structure. Through this constant, the universe maintains coherence, order, and consistency, revealing a design that is subtle, powerful, and profoundly elegant. Richard Feynman emphasized that in modern physics, what truly matters are not isolated positions or moments, but events. An event is something that happens at a specific place and at a specific time, and neither of these pieces of information is meaningful without the other. He explained that older ways of thinking encouraged people to focus on where an object was, as if space alone could tell the full story. Later, time was added as a separate label, but in reality, physics does not deal with space alone or time alone. It deals with occurrences, with things that actually happen, and these are always embedded in space, time together. Feynman liked to point out that asking only where something is can be misleading. An object does not simply exist at a location forever. It exists there at a particular moment. Likewise, asking only when something happens without specifying where leaves the description incomplete. Events are the fundamental units of reality in physics. Once this is understood, many confusions dissolve, because the universe no longer appears as a collection of objects floating in space, but as a network of interconnected happenings. He explained that focusing on events rather than positions allows different observers to describe the same reality without contradiction. Two observers moving relative to each other may disagree about the coordinates of an event, meaning they may assign different values of space and time to it. However, they agree that the event occurred. The disagreement lies only in the labels used to describe it. This shift in thinking is crucial. Physics is not concerned with labels themselves, but with the relationships between events. Feynman emphasized that the relationships between events are what carry physical meaning. For example, whether one event can influence another depends not on their individual positions or times, but on how they are separated in space-time. If an event can send a signal to another at or below the speed of light, then a causal relationship is possible. If not, no influence can occur. This way of thinking replaces vague ideas about action at a distance with a precise, testable structure. He also explained that events allow physics to remain consistent across different frames of motion. Observers may divide space, time differently into space and time, but the structure of events remains intact. The space-time interval between two events is the same for all observers, even though they may calculate it using different combinations of distance and duration. This invariant relationship gives physics its stability. It ensures that laws do not depend on who is observing or how they are moving. Feynman often used this idea to show why the universe does not need a preferred viewpoint. There is no special observer who sees events as they really are, while others see distortions. Each observer sees the same set of events from a different angle, much like looking at a landscape from different hills. The landscape does not change, only the perspective does. Events provide the common ground that unites all descriptions. He also pointed out that thinking in terms of events naturally leads to a clearer understanding of causality. Causes and effects are not abstract notions floating in time. They are events connected by allowed paths in space-time. The cause must lie within the region of space-time that can influence the effect. This removes ambiguity and prevents paradoxes. Physics does not need metaphysical assumptions about cause and effect. The structure of space. Time itself defines what is possible. Feynman emphasized that this event-based view also clarifies the role of measurement. Measurements are events too. A clock reading, a particle collision, or a detector click are all events that occur at specific locations and times. By treating measurements as events, physics avoids the mistake of assuming an external observer outside space-time. Observers and instruments are part of the same universe they observe. This reinforces the internal consistency of physical theory. He also stressed that this way of thinking helps separate what is fundamental from what is convenient. Coordinates, reference frames, and measurement systems are tools we use to describe events. They are not part of reality itself. Events are what happen. Coordinates are how we talk about them. Confusing the two leads to unnecessary debates and misunderstandings. Feynman believed that clarity in physics often comes from recognizing this distinction. In this perspective, the universe becomes a tapestry of events woven together by the threads of space, time. Objects are no longer primary entities drifting through an empty background. They are collections of events linked by continuous paths. Motion itself becomes a sequence of events forming a history in space-time. This view may feel abstract, but Feynman emphasized that it is grounded in experiment and observation. By focusing on events rather than positions, physics gains a language that is both flexible and precise. It allows multiple observers to share a common reality without forcing them to agree on arbitrary details. Events anchor physical descriptions to what actually happens, while space-time provides the structure that connects those happenings. In the end, Feynman's emphasis on events reminds us that physics is not about static snapshots of the universe, but about processes and relationships. The universe is not a frozen collection of places and moments. It is a dynamic sequence of events unfolding within space-time. Understanding this shift in perspective deepens our grasp of reality and reveals why space-time is such a powerful and necessary concept in modern physics. Richard Feynman explained that when physics speaks about gravity in the modern sense, it is no longer talking about a simple pulling force acting across empty space. Instead, gravity emerges as a consequence of the geometry of space-time itself. Massive objects do not reach out and tug on other objects in the way magnets or ropes might. Rather, they change the shape of the space-time around them, and other objects move according to that shape. This shift in understanding replaces the idea of force with the idea of structure, and Feynman found this replacement both powerful and elegant. He emphasized that this concept becomes clearer once space and time are already understood as a single entity. If space-time is the stage on which all events occur, then gravity is not something acting within that stage, but something that modifies the stage itself. Massive bodies, such as stars and planets, alter the geometry of space-time around them. Objects nearby then follow the straightest possible paths within that curved geometry. To an observer, these paths appear as curved motion, which is interpreted as gravitational attraction. Feynman often clarified that the word curved should not be taken too literally in a visual sense. Space-time is not bent into a visible arc in some higher, dimensional space that we can look at. Curvature is a mathematical description of how distances and times behave. It tells us how measurements change and how paths deviate from what would be expected in flat space-time. The usefulness of the idea lies not in visualization, but in its ability to predict how objects move and how time flows in gravitational fields. One of the most striking consequences of this view, Feynman explained, is that gravity affects time itself. Clocks closer to massive objects run more slowly than clocks farther away. This is not because gravity interferes with the clock mechanism, but because the structure of space-time is different in regions of different gravitational strength. Time flows at different rates depending on the geometry of space-time. This effect has been measured and must be accounted for in modern technology, confirming that gravity truly reshapes time. He also pointed out that free fall is a key idea in understanding gravity as geometry. An object in free fall feels no force acting on it. Astronauts orbiting the Earth feel weightless, even though gravity is very much present. Feynman emphasized that this sensation of weightlessness reveals something profound in free fall. Objects are simply following natural paths through curved space-time. The feeling of gravity arises not from being pulled, but from being prevented from following those natural paths, as when standing on the ground. Feynman liked to highlight how this perspective unifies different phenomena. The falling of an apple, the orbit of the moon, and the bending of light near a star are all explained by the same geometric principle. Light, despite having no mass, follows the geometry of space-time and therefore bends in the presence of gravity. This showed that gravity is not just about mass attracting mass, but about how space-time guides all forms of energy and motion. He emphasized that this understanding removes the need for mysterious instantaneous forces. Changes in gravity do not propagate instantly across the universe. They travel at the speed of light, in accordance with the structure of space-time. If a massive object moves or changes, the geometry of space-time adjusts, but that adjustment spreads outward at a finite speed. This preserves causality and aligns gravity with the other fundamental interactions. Feynman also noted that describing gravity as geometry does not make it less real. On the contrary, it makes gravity more deeply embedded in the nature of reality. Space-time geometry is not something added on top of physics, it is the framework within which physics operates. By understanding gravity this way, physicists gain a more unified and coherent picture of the universe. He cautioned, however, that this description is still a model, albeit a very successful one. It works extraordinarily well in explaining large-scale phenomena such as planetary motion and the behavior of stars and galaxies. Where it may need refinement is at extremely small scales or under extreme conditions. Feynman believed that good physics always remains open to improvement, even when its current models are remarkably accurate. In this view, gravity becomes less like an invisible hand pulling objects together and more like a rulebook that tells objects how to move. Space-time provides the rules, mass and energy write the geometry, and motion follows naturally. Feynman found this deeply satisfying because it reduces complexity without losing explanatory power. By seeing gravity as the geometry of space-time, we are invited to rethink our intuitive ideas about force and motion. The universe is not held together by hidden strings of attraction, but by a structured and responsive fabric that shapes how events unfold. This understanding not only clarifies gravity itself, but also strengthens the idea that space-time is the fundamental arena of physical reality, shaping everything from the fall of a stone to the movement of galaxies. Richard Feynman emphasized that once space-time is understood as the framework of reality, cause and effect can no longer be thought of as simple sequences ordered by a universal clock. Instead, causality is shaped and limited by the structure of space-time itself. Events are not free to influence one another arbitrarily. The geometry of space-time determines which events can be connected by cause and effect, and which must remain forever unrelated. This realization transforms causality from a philosophical idea into a physical one. He explained that the speed of light plays a central role in defining causal relationships. Because no signal or influence can travel faster than light, there are strict boundaries on how events can affect each other. For any given event, there is a region of space, time that can influence it and a region that it can influence. Events outside these regions are causally disconnected. This structure is not imposed by human logic, it is enforced by the fundamental laws of nature. Feynman stressed that this limitation does not weaken the universe but gives it coherence. Without such limits, cause and effect could become tangled, allowing contradictions such as effects appearing before causes. Space-time prevents this. Events that can influence one another always preserve the same order for all observers. Even though observers may disagree about the timing of distant events, they never disagree about the order of events that are causally linked. This protects the consistency of physical law. He also emphasized that not all disagreements about event order matter physically. Two observers moving differently may disagree about which of two distant, unrelated events happened first. Feynman explained that this disagreement has no physical consequence because the events cannot influence each other anyway. The structure of space-time naturally separates meaningful orderings from meaningless ones. Only when influence is possible does ordering become physically significant. Feynman often highlighted that this understanding removes the need for hidden or instantaneous influences. In older thinking, forces like gravity were sometimes imagined to act instantly across vast distances. Modern physics, grounded in space-time, rejects this. Changes in physical conditions propagate at finite speeds. If something changes, its influence spreads outward through space-time, respecting the speed of light. This ensures that causality remains intact even in a dynamic universe. He also connected this idea to the concept of prediction. Physics is powerful because it allows us to predict future events from past ones. These predictions rely on causal connections. Space-time tells us which past events are relevant for predicting a given future event. Only events within the region of space-time that can influence the future event matter. Everything else, no matter how dramatic, is irrelevant. This sharply defines the limits of prediction and removes unnecessary complexity. Feynman emphasized that observers themselves are part of this causal structure. Observations are events that occur at specific points in space-time. An observer cannot receive information from events that lie outside their causal reach. This may seem obvious, but it has deep implications. It means there is no privileged observer who can see the entire universe at once. Knowledge itself is constrained by space-time. He also pointed out that causality in space-time is not merely about forbidding faster than light signals. It also shapes how physical theories are built. Equations must respect causal order. A theory that allows effects to precede causes would not just be strange, it would be physically unacceptable. Space-time acts as a guiding principle, ensuring that theories remain grounded in reality. Feynman liked to emphasize that this structure gives the universe a kind of logical discipline. Even though space-time allows for flexibility in measurements of space and time, it enforces strict rules about influence. Observers may disagree about distances and durations, but they cannot disagree about causal connections. This balance between flexibility and rigidity is one of the hallmarks of space-time. He also addressed common misunderstandings about determinism. The causal structure of space-time does not imply that everything is predetermined in a simple way. It simply defines what can influence what. Within those limits, events may still involve uncertainty, probability, and randomness, especially at the quantum level. Space-time sets the stage for causality but does not dictate every outcome. Feynman emphasized that understanding causality in this way changes how we think about the universe as a whole. The universe is not a place where everything is instantly connected to everything else. It is a structured network of events linked by allowed paths of influence. This structure gives the universe both order and openness. It allows change and interaction while preventing contradiction. In this view, cause and effect are not imposed from outside the universe as abstract principles. They arise naturally from the geometry of space-time. The universe enforces its own logic through its structure. Feynman found this deeply satisfying because it showed that the laws of physics are not arbitrary rules, but expressions of how reality is built. By recognizing that causality is shaped by space-time, we gain a deeper appreciation of why the universe behaves consistently even when our intuitions fail. Space-time does not merely host events, it organizes them. It determines which events can matter to one another and which cannot. This insight strengthens our understanding of reality and reveals the quiet but powerful role that space-time plays in maintaining the coherence of the universe. Richard Feynman consistently reminded his audiences that space-time, despite its power and success, is not a picture of reality in the everyday sense, but a model. It is a carefully constructed framework designed to organize observations and make accurate predictions. He warned against the temptation to imagine space-time as a tangible substance or a visible object. Physics does not deal in literal pictures of what the universe looks like. Behind the scenes, it deals in descriptions that work. Space-time is one of those descriptions, and its value lies in its effectiveness, not in its visual appeal. He emphasized that models in physics are not meant to satisfy intuition. They are meant to reflect how nature behaves. Human intuition evolved in a world of slow speeds and weak gravity, and it is not equipped to grasp the true structure of the universe at all scales. When space-time feels strange, that strangeness is not a failure of the model. It is a reminder of the limits of intuition. Feynman believed that demanding comfort from a model is a mistake. Demanding accuracy is not. Feynman often explained that confusion arises when people mistake the model for the thing itself. Space-time is not something that exists independently as a material fabric you could point to or step outside of. It is a mathematical structure that allows physicists to relate events to one another consistently. When people ask what space-time is made of, Feynman would caution that this question may not be meaningful. Models are judged by what they explain and predict, not by whether they resemble familiar objects. He also stressed that space-time is not unique in this respect. Many successful ideas in physics are models that defy everyday visualization. Fields, wave functions, and forces are all descriptions, not physical objects in the ordinary sense. Space-time belongs to this same category. It is a way of encoding relationships between events. Expecting it to behave like a physical substance leads to unnecessary metaphysical puzzles. Feynman emphasized that the strength of the space-time model lies in its unifying power. It brings together motion, time, distance, gravity, and causality under a single framework. A good model, in Feynman's view, is one that reduces complexity by revealing deep connections. Space-time does exactly that. It replaces a collection of separate rules with a coherent structure. This does not mean it is the final word, but it does mean it is a remarkably successful one. He also reminded his listeners that models evolve. Newton's model of space and time worked extremely well for centuries before its limitations were discovered. It was not wrong within its domain, it was incomplete. Space-time extends Newton's ideas rather than destroying them. In everyday situations, Newton's picture is still sufficient. Space-time becomes necessary only when greater accuracy is required. This layered nature of models is a sign of progress in physics, not inconsistency. Feynman stressed that treating space-time as a model encourages openness. If future experiments reveal phenomena that cannot be explained by current space-time descriptions, physics will adapt. New models will be built, perhaps extending or reshaping space-time. Clinging to a model as absolute truth would block that progress. Feynman believed that the willingness to abandon even the most successful ideas is one of science's greatest strengths. He also pointed out that space-time does not explain everything. It provides a framework, not a complete account of reality. Within that framework, questions about matter, energy, and quantum behavior still require additional theories. Expecting space-time to answer all questions leads to disappointment. Understanding its role as a model helps place it in proper context. Feynman emphasized that the usefulness of a model is measured by experiment. Space-time earns its place in physics because its predictions match observations with extraordinary precision. Time dilation, gravitational time shifts, and the bending of light have all been measured. These successes justify the model, regardless of whether it feels intuitive. In physics, agreement with experiment outweighs aesthetic preference. He also warned against overinterpreting metaphors. Comparing space-time to a fabric or rubber sheet can help with intuition, but such images can mislead if taken too seriously. Metaphors are teaching tools, not literal descriptions. The real content of the model lies in its mathematical relationships and empirical consequences. Feynman believed that clarity comes from knowing where metaphors stop being useful. By insisting that space-time is a model, Feynman reinforced a broader lesson about science. Science does not claim to reveal ultimate reality. It offers increasingly accurate descriptions of how nature behaves. These descriptions are provisional, always open to refinement. Space-time represents a powerful step in that ongoing process, not its conclusion. In this light, space-time becomes less mysterious and more honest. It does not pretend to be a picture of what the universe really is. It is a tool that works extraordinarily well. By using it wisely, without confusing it for absolute truth, physicists can continue to explore deeper layers of reality. Feynman's final message in this keynote is one of intellectual humility. The universe is under no obligation to be easily visualized. Our responsibility is not to demand comfort, but to build models that faithfully reflect observation. Space-time succeeds because it does exactly that. It organizes complexity, preserves consistency, and remains open to revision. In recognizing space-time as a model, not a picture, we align ourselves with the true spirit of science and keep the door open to future discovery.